On April 10, 2019, astronomers released the first horizon-scale image of a black hole. But the black hole itself was not the orange ring. The ring was radio light from hot material around M87 star, while the dark center was a shadow shaped by gravity and captured light. That makes the image a useful place to begin because the same problem returns across cosmology. How much can we know about parts of the universe that ordinary light cannot show us? M87 star lies about 55 million light-years away and contains about 6.5 billion times the mass of the Sun. The famous image was not a photograph of a surface because a black hole does not provide one for a camera to record. The Event Horizon Telescope measured radio light from extremely hot material near the black hole, and gravity bent the paths of that light while some photons traveling too close were captured. That dark region is usually called the black hole's shadow. The name is useful, as long as we remember what kind of shadow it is. It is not a solid black disk floating in front of glowing gas, and its visible boundary is not simply a photograph of the event horizon itself. The shadow is an optical consequence of the way light moves through strongly curved space-time around it. The event horizon lies deeper within this geometry. What appears in the image is a larger dark depression produced by the combined effects of light bending and photon capture. This distinction matters because the image is already telling us something subtle about astronomy. We are looking at an object that cannot be seen directly, and yet its presence has left a shape in the light around it. Even making that shape visible required an unusual kind of telescope. The Event Horizon Telescope is not one dish sitting beneath a single dome. During the observations used for the first M87 image, radio observatories in different parts of the world worked together through a technique called very long baseline interferometry. By comparing the radio signals recorded at widely separated sites, astronomers created the resolving power of a virtual telescope roughly the size of Earth. The observations were made at a wavelength of about 1.3 millimeters, giving the array enough angular resolution to distinguish structure around the source that would otherwise blur into a single unresolved source. And even then, the telescope did not collect a neat picture one pixel at a time. Each pair of observing sites measured part of the information carried by the incoming radio waves. The Earth's rotation changed the geometry of those pairs during the observing period, helping the array sample more of the signal. But there were still gaps, because there were not telescopes covering every possible point on the planet. The final image, therefore, had to be reconstructed from incomplete measurements. The collaboration, therefore, tested the reconstruction carefully. Separate imaging teams used different methods, and the data were also compared with synthetic observations of known model images. Across those approaches, the same basic structure returned, an asymmetric ring about 42 microarcseconds across with a deep central reduction in brightness. In other words, the famous picture is not important because one algorithm happened to draw a convincing circle. Its important features survive different ways of reconstructing the measurements. There is something appropriate about that. A black hole is defined by a limit on what can come back out, and its first horizon-scale image was assembled from information gathered across an entire planet. No single telescope saw the ring. The structure emerged because many separated measurements agreed. The bright part is easy to mistake for a glowing rim attached to the black hole. It is not. The light comes from hot plasma moving around the black hole, and relativistic motion makes part of the ring appear brighter than the rest. The central darkness is different. It does not glow because there is no luminous surface waiting there to be revealed with a longer exposure. A black hole can influence light, matter, magnetic fields, and the motion of nearby plasma, but once we begin talking about the region beyond the event horizon, we have crossed into a part of spacetime from which ordinary outward signals cannot reach a distant observer. For now, it is enough to stay outside that boundary. Imagine light taking different routes around it. Some rays pass far enough away to escape with only modest bending. Others pass closer and are deflected much more strongly. Some can circle the black hole before escaping, while others are captured. What reaches us is the light that survived this curved region of space-time, and then crossed roughly 55 million light-years to Earth. The image we receive is shaped partly by what arrived and partly by what did not. That is where this story begins to widen. Astronomy is often described as the science of light, and for good reason. Nearly everything we know about distant stars and galaxies began with some form of radiation reaching a detector. But black holes introduce a strange limit to that method. They force us to ask how much can be learned from an object whose defining boundary prevents information from returning in the usual way. The first image of the black hole did not remove that limit. It did something more interesting. It showed that a boundary can leave evidence on the space around it. The black hole's gravity changes the paths of photons. The surrounding plasma changes its brightness as it moves. The missing light at the center produces a measurable structure. We cannot simply look through the darkness, but we can study the way the darkness changes what remains visible. Later Event Horizon Telescope observations have continued to recover a ring of similar size around the M87 black hole, even while the brightest part of the ring has shifted. The surrounding plasma can vary, but the shadow scale structure persists. So the quiet question is not whether the black hole is there. The evidence for that is now exceptionally strong. The more useful question is what kind of knowledge is possible when the thing we want to understand sits behind a boundary that light cannot cross outward. We can measure the glow around it. We can follow matter moving nearby. We can compare the shape of the shadow with the predictions of general relativity. We can watch the environment change from one observing campaign to another. But there is still a line in the geometry, beyond which the familiar idea of simply receiving a signal from the object stops working. That line is called the event horizon. Once we understand why the event horizon behaves as a boundary, the black hole becomes the first example of a much larger idea. The universe also contains limits set by travel time, by the opacity of the early cosmos, and by the expansion of space itself. In each case, the central question is what information can reach us at all, even after telescopes improve. But we do not need to hurry toward any of those yet. For a little while longer, we can stay with this single orange ring, suspended against a dark field, and notice what it actually represents. It is a pattern made by light at the edge of what light can tell us. That is a gentle place to begin, because the deepest mysteries in astronomy are not always found by looking farther. Sometimes they appear when we discover where looking stops. The event horizon is where looking stops, but it helps to be careful about what that sentence means. A black hole does not have a surface like a planet or a star. If you could somehow approach a sufficiently large black hole while protected from the hot material around it, you would not find a wall waiting at the horizon. There is no shell to touch and no line painted across space. In general relativity, the event horizon is a boundary in spacetime, defined by which future paths can still communicate with the universe outside. Far from a black hole, this is easy to picture. If you switch on a flashlight and aim it away from the black hole, the light travels outward. Aim it sideways and it takes another path. Aim it inward and it falls toward the black hole. There are still directions available that lead away. As you move closer, gravity changes those possibilities. Einstein's description of gravity does not treat it as an invisible force pulling objects through an otherwise fixed stage. Matter and energy affect the geometry of spacetime itself, and objects moving freely follow paths through that geometry. Light does the same. A beam of light can be bent even though it has no rest mass, because the space-time through which it travels is curved. Near a black hole, that curvature becomes extreme. One useful way physicists visualize this is with something called a light cone. You do not need to picture an actual cone floating in space. It is simply a diagram showing the directions that light, and therefore any slower physical signal, can travel from a particular event. Far away, some of those possible future directions point outward. Closer to the black hole, the geometry changes how those future paths are arranged. At the event horizon, the boundary between escape and capture has been reached. Beyond it, every future directed path available to light remains inside the black hole. This is why saying that light is simply being pulled too hard can be misleading. Light locally still moves at the speed of light. The structure of space-time no longer provides a future route leading back to the distant exterior. Once something has crossed the horizon, sending a message outward would require a path that the geometry does not allow. And that is what makes the horizon an information boundary. There is a familiar thought experiment that makes the idea easier to hold. Imagine that a small probe is falling toward a black hole and transmitting a radio pulse once every second according to its own clock. At first, the pulses reach you normally. As the probe falls deeper into the gravitational field, the signals arriving far away become increasingly delayed and redshifted. Their wavelength stretches, and their energy falls, so the probe appears to slow and fade as the light carrying information about it struggles through the strongly curved region around the horizon. From the probe's own point of view, however, the story is different. Its clock continues ticking. In the classical description of a sufficiently large black hole, crossing the event horizon does not require an infinite amount of the probe's own time. The horizon itself is not a place where a freely falling observer must encounter a physical barrier. If the black hole is large enough, and the surroundings are quiet enough, there need not even be an obvious local signal announcing the exact moment of crossing. The strange behavior belongs to the relationship between different observers and to the geometry connecting them. This is one reason black holes resist ordinary intuition. We are used to boundaries being local things. A shoreline can be touched. A door can be crossed and then crossed again. Even the surface of the sun is associated with matter that becomes opaque enough for us to define a visible layer. An event horizon is different. Its meaning depends on the future of possible signals. If a flash of light begins outside the horizon and points in the right direction, it can still reach distant space. If it begins inside, there is no future-directed route that eventually carries it back to an observer far away. For the simplest non-rotating black hole, the geometry can be described with the Schwarzschild solution to Einstein's equations. Real astrophysical black holes are expected to rotate, so their geometry is more complicated, but the essential feature survives. There is still an outer horizon acting as a one-way causal boundary. Matter, light, and the information they carry can cross inward, but after that crossing, those signals do not return to the external universe. The black hole still has observable exterior properties. From outside, astronomers can infer its mass. They can study the motion of surrounding material. They can learn about its rotation. They can examine magnetic fields near the accretion flow and compare the behavior of light with predictions from general relativity. The black hole continues to affect everything around it gravitationally. What the horizon prevents is a more specific kind of knowledge. It prevents us from receiving a direct message sent from an event after that event has occurred inside the horizon. That difference will matter again later, because astronomy contains several kinds of darkness. There are things we cannot see because they emit almost no light. There are things hidden behind matter that blocks certain wavelengths. There are things so distant that their light has not had enough time to reach us. And then there are boundaries built into the causal structure of space-time itself. A black hole introduces us to the last kind. It is tempting at this point to ask what lies at the center, because the equations of classical general relativity lead toward a singularity. But that question belongs farther down the road. General relativity itself tells us that the horizon and the central singularity are not the same thing, and the physics expected near a singularity enters territory where a complete theory of quantum gravity may be required. For now, the horizon gives us enough to think about. It divides events that can still send information to distant observers from events that cannot. And remarkably, the universe does not require us to see through that boundary in order to learn that the black hole exists. We can watch stars orbit unseen masses. We can observe gas heating as it spirals inward. We can measure the distorted light around the shadow. Each of these carries information about the gravitational field outside the horizon. There is another messenger as well, one that does not rely on glowing plasma or starlight. Einstein's equations predict that accelerating masses can disturb space-time itself, sending changes outward as gravitational waves. For a long time, those waves were far too faint for us to measure directly. Then, after decades of increasingly sensitive experiments, detectors on Earth recorded a signal that lasted only a fraction of a second. The source was two black holes circling one another rather than a shining star or an exploding cloud of gas. They moved faster as their orbit tightened until they merged into a single black hole. Nothing had escaped from inside either event horizon. The information reached us because the space-time outside those horizons was changing. And that gives us a second way of listening to something we cannot see. 4 years before the orange ring around M87 was shown to the world, black holes had already revealed themselves in a completely different way. The signal arrived on September 14, 2015. At the LIGO Observatory in Livingston, Louisiana, an instrument recorded a tiny change in the relative lengths of two long perpendicular arms. A second observatory in Hanford, Washington, recorded almost the same pattern about 7 milliseconds later. The disturbance lasted only a fraction of a second. Its frequency rose as it passed through the detectors, beginning at around 35 Hz and climbing rapidly as the signal grew stronger. There was no flash of visible light associated with the event for LIGO to photograph. The source was about 1.3 billion light-years away, and the information arriving on Earth had been carried by something astronomy had never directly detected before: a gravitational wave. To understand what LIGO measured, it helps to return for a moment to the geometry we were considering around the event horizon. General relativity describes gravity through the shape of space-time. A planet changes that geometry slightly. A star changes it more. A black hole changes it enough to create an event horizon. But the geometry does not have to remain perfectly still. When massive objects accelerate in certain ways, changes in the gravitational field can propagate outward as gravitational waves. The easiest sources for us to detect are therefore not quiet objects sitting alone. They are systems in which enormous masses are moving rapidly, such as two black holes orbiting one another before a merger. The wave that eventually reaches Earth is extremely weak. It does not push a detector sideways like wind against a building. Instead, as a gravitational wave passes, it produces a very small alternating stretch in one direction and compression in the perpendicular direction. LIGO was designed to measure that pattern. Each of its two observatories contains an enormous L-shaped interferometer. The two arms are each 4 kilometers long and contain vacuum tubes with mirrors positioned at their ends. A laser beam enters the instrument and is divided into two paths. One part travels along one arm, while the other travels along the perpendicular arm. Mirrors reflect the light repeatedly, allowing it to travel a much greater effective distance before the two beams are eventually brought back together. If the two paths remain unchanged, the returning light waves can be arranged to interfere in a predictable way. But if a gravitational wave passes through the observatory, it changes the relative light travel time along the two perpendicular directions. The difference is unimaginably small in everyday terms, yet the interference between the returning laser beams allows that change to be measured. But the shape of this contained far more than the simple fact that something had happened. It carried a record of motion. The two black holes had been orbiting each other. As they emitted gravitational waves, energy was carried away from the binary system. Their orbit gradually became smaller, which caused the black holes to circle each other more quickly. As their speed increased, the frequency of the gravitational waves increased as well. This produced the rising signal recorded by LIGO. Over roughly 0.2 of a second in the most visible part of the detection, the measured waves increased rapidly in both frequency and amplitude. That pattern could be compared with solutions of Einstein's equations describing two compact objects spiraling inward. The match allowed researchers to reconstruct a system they had never seen. One black hole had a mass of roughly 36 suns. The other was roughly 29 times the mass of the Sun. They approached one another faster and faster until, during the final fraction of a second, they merged. What remained was a single black hole with a mass of about 62 suns. The numbers do not add up to 65 because some of the system's mass was converted into energy carried away by gravitational waves. Roughly 3 solar masses were radiated in that form during the merger. For an extraordinarily brief interval, an event that produced no ordinary light for us to observe sent an immense amount of energy outward through the geometry of space-time itself. And the signal kept changing even after the two original black holes had become one. The newly formed black hole was initially disturbed. It settled toward a stable state while producing a final fading pattern known as ring-down. The complete signal therefore carried traces of 3 stages: the inward spiral, the merger, and the settling of the remnant. Astronomers had not photographed any of them. They reconstructed the event from the waveform that reached Earth. Gravitational waves also behave differently from light as they cross the cosmos. Light can be absorbed, scattered, blocked by dust, or altered as it passes through matter. Gravitational waves interact so weakly with ordinary material that they can travel through intervening matter and galaxies with very little disturbance. The same weakness that makes them valuable also makes them extraordinarily difficult to detect. A gravitational wave can cross Earth with almost nothing happening to it. That allows ancient information to survive its journey, but it also means that a detector must be sensitive to changes far smaller than anything our bodies could notice. The two LIGO observatories are separated by thousands of kilometers, partly because a real astronomical signal should appear in more than one detector, with a timing difference consistent with a wave crossing Earth. That is what happened in September of 2015. Livingston recorded the signal first. Hanford recorded the corresponding signal about 7 milliseconds later. The waveforms agreed after accounting for the different locations and orientations of the instruments. Researchers also compared the observations with gravitational wave models and studied the detector environment to rule out terrestrial disturbances that might imitate an astrophysical event. The conclusion was that the signal had come from the merger of two black holes. For the first time, humanity had directly detected gravitational waves. And with that detection, astronomy gained something fundamentally new. For nearly all of its history, astronomy depended on electromagnetic radiation. Human eyes used visible light. Radio telescopes extended that sense into longer wavelengths. Infrared, ultraviolet, X-ray and gamma-ray observatories opened other parts of the same electromagnetic spectrum. Each new wavelength revealed objects that had been hidden from the wavelengths we used before. Gravitational wave astronomy is different. It does not simply give us another color of light. It gives us another carrier of information. A pair of black holes can therefore remain almost completely dark in the electromagnetic sky while being unmistakably present in gravitational wave data. Their masses can be estimated. Their orbital motion can be followed through the changing frequency. Their merger can be recognized in the waveform, and the settling of the final object can be compared with predictions from general relativity. The universe has become observable in a way that does not require it to shine. That changes the meaning of invisibility. An object can be dark and still reveal its motion. It can be hidden from an optical telescope while producing a measurable disturbance in space-time. And a boundary that prevents light from returning does not erase every trace of what the object does to the region outside it. Once we begin thinking about astronomy in terms of information, darkness becomes less simple than it first appeared. Sometimes darkness means that nothing is emitting visible light. Sometimes it means that light has been absorbed before reaching us. Sometimes it means that the source communicates through something we had not yet learned how to measure. But there is another kind of darkness waiting much farther back in cosmic history. If we use ordinary telescopes and look deeper into space, we also look backward in time. Galaxies become younger, their stars become more primitive, and eventually the familiar structures of the modern universe disappear. We might imagine that a sufficiently sensitive telescope could continue this process indefinitely, allowing us to watch the universe all the way back toward its beginning. But light itself eventually encounters a limit. There was a time when the universe was filled with matter so hot and ionized that photons could not travel freely across it. Instead of crossing space for billions of years as they do now, light repeatedly scattered from charged particles. The early universe was opaque. And when it finally became transparent, the light released into that new transparency began a journey that is still ending on our detectors today. It is the oldest light we can receive. The oldest light we can receive does not come from a star. It does not come from the first galaxy either, because the universe was already hundreds of millions of years old before galaxies became common enough for their light to fill the young cosmos. The light we are looking for began traveling much earlier, when there were no planets, no stars, and no familiar structures in the sky. If we could move backward through cosmic history using an ordinary telescope, distant galaxies would gradually appear younger. Their stars would change. Their shapes would become less settled. Eventually, we would reach a period before any galaxy had formed. But we could not simply keep going until we watched the Big Bang itself. About 380,000 years after the beginning of cosmic expansion, something happened that placed a natural boundary on how far back ordinary light can show us. Before that time, the universe was much hotter and much denser than it is today. Matter existed largely as a plasma, with atomic nuclei and free electrons moving through an intense sea of radiation. Photons were everywhere, but they could not travel very far in a straight line. Free electrons interacted readily with them, scattering the light again and again. A photon might move for a short distance, encounter an electron, change direction, and continue only to be scattered once more. There was plenty of light throughout the early universe, but it was not yet transparent. This is an important distinction because the early universe was not dark in the way an empty room is dark. It was closer, in one limited sense, to looking through a dense glowing fog. Radiation existed throughout the plasma, but information carried by individual photons could not travel freely across large distances. As the universe expanded, it cooled. Eventually, the temperature fell far enough for electrons to remain bound to atomic nuclei, producing neutral atoms, mostly hydrogen and helium. Cosmologists call this period recombination, although the name comes from historical terminology rather than from atoms literally combining for a second time. Once enough free electrons had been removed from the plasma, photons stopped scattering so frequently. Space became transparent over great distances. The photons that last scattered during this transition were finally able to travel freely through the expanding universe. Many of those photons are still traveling, and some are reaching us now as the radiation we call the cosmic microwave background. As space expanded, the wavelengths of the traveling radiation expanded as well. Radiation that once belonged to a much hotter environment was stretched toward longer wavelengths. Until today, we detect it primarily in the microwave part of the electromagnetic spectrum. Its average temperature is now only about 2.7 Kelvin, just a few degrees above absolute zero. And yet it comes from almost every direction. If you could see microwave radiation with your eyes and remove the foreground emission from our own galaxy and other nearby sources, the sky would not become black between the stars. A faint background would surround you. Every direction would lead eventually toward a surface in the distant past from which this ancient radiation has been traveling. It is tempting to imagine that surface as a physical shell surrounding Earth, but there is no special spherical wall located somewhere out in space. The appearance of a shell comes from our position as observers. When we look farther away, we also look farther backward in time because light requires time to travel. In every direction, there is a distance corresponding to the era when the universe became transparent. The photons arriving from those regions have been traveling toward us ever since. Cosmologists often call it the surface of last scattering. But for understanding what telescopes can see, the essential result is simple. Ordinary electromagnetic radiation cannot give us a direct image of earlier times in the same way it gives us images of galaxies. If we build a larger optical telescope, we may see fainter galaxies. If we build a more sensitive infrared telescope, we may detect galaxies from earlier cosmic history. If we improve our radio instruments, we can study other faint signals across enormous distances. But when we reach the era before the universe became transparent, simply collecting more ancient photons of the same kind no longer solves the problem. The universe itself was opaque to freely traveling light. This makes the cosmic microwave background another kind of information boundary. It is very different from the event horizon of a black hole. A black hole horizon is a causal boundary in spacetime, a region beyond which outward signals cannot reach a distant external observer. The early universe presents a different obstacle. Photons existed before recombination, but they interacted so frequently with the plasma that they could not carry a direct image across the cosmos to us. The result, however, feels strangely similar from where we sit. We can receive light from the boundary. We cannot use that light to look straight through it. And yet, once again, the boundary does not mean that everything earlier is beyond science. The cosmic microwave background is almost uniform, but not perfectly uniform. Across the sky are tiny differences in temperature. Some regions are slightly warmer than average, while others are slightly cooler. The differences are extremely small, measured in roughly parts per 100,000, but their pattern contains information about conditions in the young universe. Those variations are connected to small differences in density. Over cosmic time, gravity amplified those early differences. Regions containing slightly more matter attracted more matter. What began as tiny irregularities eventually contributed to the enormous web of galaxies and clusters that fills the observable universe today. The smooth microwave sky therefore contains the beginnings of structure. This is one reason missions such as NASA's Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the European Space Agency's Planck mission spent years measuring this radiation with increasing precision. Each generation revealed finer detail. Planck eventually mapped temperature variations across the entire sky at high resolution, along with measurements of the polarization of the radiation. Cosmologists use patterns in those observations to test models of the universe and estimate properties such as its age, composition, geometry, and expansion history. So we are doing something that seems almost contradictory. We have reached a wall for ordinary light, but the wall itself is covered in information. The photons cannot show us a photograph of what happened before recombination. They can, however, carry evidence produced by physical conditions that existed before they traveled freely. The pattern of the cosmic microwave background was shaped by processes taking place in the early plasma. Matter and radiation interacted. Gravity influenced regions with different densities. Pressure in the hot plasma resisted compression, allowing waves to move through the primordial mixture before recombination preserved their imprint in the radiation. By measuring the pattern left behind, cosmologists can work backward. This is not the same as seeing the earlier universe directly. It is inferring a surviving record, a distinction that is becoming familiar. Around M87, we did not see through the black hole's horizon. We studied light shaped by the gravitational environment outside it. With LIGO, we did not photograph two distant black holes. We reconstructed their motion from gravitational waves reaching Earth. Now the cosmic microwave background gives us another surviving record, this time covering nearly the entire sky. Three very different observations have begun to suggest the same quiet idea. These observations point toward a quiet idea. Astronomy can learn without receiving a direct image, because a waveform or a pattern preserved on ancient light can reveal properties of things that are not directly visible. The cosmic microwave background takes that principle almost as far backward in time as electromagnetic astronomy can go. Beyond its surface of last scattering, light no longer gives us a clear direct view. But there is another way that invisible things can reveal themselves, and it does not require us to travel backward toward the beginning of time. We can find it in the galaxies around us today. There are places where stars move as though more matter is present than the matter we can see. There are galaxy clusters where the paths of background light bend under the gravity of mass that does not appear in ordinary images. Across the universe, visible objects keep responding to something that remains dark. This time, the missing information is not hidden behind an ancient fog. It appears to be sitting inside the structures we can already see. And we know it is there because of what it does to the light passing around it. The light of a distant galaxy can tell us something about an object that has never produced any light of its own. That sounds unusual at first, but the idea follows naturally from the black holes we have already visited. Gravity changes the paths taken by light. If enough mass lies between us and a distant source, space-time around that mass can bend the source's light before it reaches us. Astronomers call this gravitational lensing. But gravitational lensing is more than a way of producing unusual pictures. The amount of distortion depends on mass. And that means the bent light can be used to weigh something we cannot see. This becomes important when astronomers study galaxies and galaxy clusters, because the visible material does not always provide enough gravity to explain what is happening. The first clues appeared long before anyone could make detailed maps of gravitational lensing. In galaxies, stars orbit around a common center. If most of a galaxy's mass were concentrated where most of its visible matter is concentrated, then stars far from the center should respond accordingly as their distance increases. But observations of many galaxies showed that their outer regions were moving in a way that implied considerably more mass than the visible stars and gas could account for. Something appeared to extend far beyond the bright part of the galaxy. The natural description became a dark matter halo, a much larger distribution of unseen mass surrounding the visible galaxy. The word dark can be slightly misleading because it sounds like a description of color. Dark matter is not simply ordinary matter painted black. As far as present observations show, it does not emit, reflect, or absorb enough electromagnetic radiation for telescopes to detect it directly in the way they detect stars, dust, or glowing gas. Its presence is inferred through gravity, which is why lensing is so useful. Light from those background galaxies begins traveling toward us. On its journey, it passes near the foreground cluster. The cluster's mass curves space-time, so the light follows altered paths before eventually reaching our telescopes. The background galaxies then appear distorted. But the more common distortions can be far smaller. A single background galaxy already has its own shape, so a tiny stretch caused by foreground mass can be difficult to identify in isolation. Astronomers therefore examine large populations of galaxies. Small statistical alignments in their apparent shapes can reveal the gravitational influence of mass distributed between those galaxies and us. This weak gravitational lensing gives astronomers a strange kind of map. The map is not built from light produced by the matter being mapped. It is built from changes in light coming from somewhere else. If the background galaxies are distorted in a particular pattern, researchers can work backward from those distortions and estimate how mass is distributed through the foreground region. Visible galaxies account for some of that mass, and hot gas accounts for more. But in many clusters, the gravitational map requires much more mass than either component provides. The unseen part is attributed to dark matter. On the largest scales, dark matter appears to form much of the underlying structure around which ordinary matter gathers. Current cosmological measurements indicate that it accounts for the great majority of matter in the universe, even though we still do not know what the dark matter itself is made of. One of the clearest places to see why this distinction matters is a system usually called the bullet cluster. It is actually a collision between galaxy clusters. The collision gives astronomers an unusual opportunity because different components of the clusters behave differently as they pass through one another. The galaxies themselves are separated by enormous distances, so many of them pass through the collision with relatively little direct interaction. The hot gas is different. Gas particles interact electromagnetically. During the collision, the vast clouds of hot gas from the clusters encounter one another, slow down, heat up, and can be observed in X-rays. That gives astronomers one map of where much of the ordinary matter is located. Gravitational lensing provides another map. By examining how background galaxies are distorted, researchers can infer where most of the total gravitational mass lies. And the two maps do not line up. The hot X-ray gas, which contains much of the ordinary matter in the clusters, is displaced from the regions where lensing indicates most of the mass is concentrated. Those mass concentrations remain closer to the galaxies that pass through the collision. The simplest dark matter interpretation is that most of the mass belonged to a component that did not slow down with the colliding gas. It moved through the encounter much more like the galaxies did. This separation between ordinary matter and the dominant gravitational mass made the bullet cluster especially important evidence for dark matter. Once again, nothing in the image shows dark matter glowing. The dark matter map is an inference constrained by several observations. X-ray data locate the hot gas, optical images locate many of the galaxies, and gravitational lensing shows where enough mass is concentrated to bend the background light by the measured amounts. The power comes from putting those different observations together. It is another example of several messengers describing the same place. And it returns us to the question we began asking beside the black hole. What can we know about something that refuses to appear directly in an image? But there is still an important boundary between knowing what something does and knowing what it is. Dark matter makes that boundary unusually clear. We know that an unseen gravitational component is required by a large body of astronomical and cosmological evidence. We do not yet know its underlying nature. The darkness here is therefore different from the darkness of a black hole. A black hole hides a region behind an event horizon. Dark matter appears dark because it does not interact with electromagnetic radiation in the ordinary ways that make matter visible to telescopes. And both are different again from the early universe, where repeated scattering prevented light from carrying a clear image through the plasma before recombination. These are three kinds of invisibility with different physical causes, and astronomy has learned a different way to work without a direct picture in each case. Near a black hole, we study the effect of gravity on surrounding light and matter. In a black hole merger, we listen to gravitational waves. At the surface of last scattering, we examine a pattern preserved in ancient microwave radiation. With dark matter, we trace the response of galaxies and the bending of background light. The universe keeps removing the simple option of looking straight at the thing we want to understand. But each time, some information remains outside the darkness. That is the distinction worth carrying with us, because invisibility by itself does not tell us how much can be learned. An object can reveal its presence through gravity, even when it does not shine. Sometimes light cannot travel freely from the place we want to see, but a surviving pattern preserves information about what came before. And sometimes a boundary prevents a particular kind of signal while leaving other measurable effects outside it. This has allowed us to move remarkably far without ever leaving our own small region of the cosmos. But the next boundary is larger. So far, every example has involved something inside a universe whose basic history we have taken for granted. Black holes form within it. Gravitational waves cross it. Dark matter helps shape its galaxies. The cosmic microwave background preserves an early stage of it. Eventually, we have to ask about the history containing all of those things. When cosmologists say that the universe was once hotter, denser, and smaller in scale, they are not simply telling a story about a distant object. They are describing the past of the space in which every observable galaxy now exists. If we continue running that history backward, the density rises, the temperature rises, and our familiar descriptions are pushed into increasingly extreme conditions. This is where the phrase Big Bang enters the story. But it brings a common misunderstanding with it. There is no observed point in empty space where every galaxy was once packed together, and from which matter later exploded outward into a waiting darkness. The evidence describes the expansion of space itself, and if we follow that expansion far enough backward, we eventually reach another limit on what our observations can tell us directly. This boundary is buried in the history of the entire observable universe. If we could follow the history of every galaxy backward, we would not find them converging on one location somewhere in the sky. There is no distant point toward which we could aim a telescope and say that this is where the Big Bang happened. The expansion belongs to the universe itself. This is easy to misunderstand because the phrase Big Bang suggests an explosion. An ordinary explosion begins at a particular place. Material moves outward through space, and if you could trace every fragment backward, you would eventually find the center of the event. Cosmic expansion does not work that way. On sufficiently large scales, distances between regions of the universe change with time. Galaxies that are not held together by local gravitational binding participate in that changing cosmic geometry, so widely separated galaxies can become farther apart without needing to be flying away from one central location through some pre-existing emptiness. The measurements that led cosmologists toward this picture began with light. When astronomers examine distant galaxies, features in their spectra are often shifted toward longer wavelengths. This cosmological redshift is closely connected to the expanse of space during the time that the light has been traveling. The farther away we look, the longer that journey has usually lasted, and the farther back in cosmic history we are seeing. That gives astronomy a peculiar relationship with distance, because looking outward also means looking backward. A galaxy whose light has traveled for billions of years is being shown to us as it was billions of years ago. We do not see its present condition. We see an old message that has only now arrived. If we gather many such messages and combine them with other observations, a pattern emerges. The universe is expanding today. The cosmic microwave background tells us that it was once much hotter and denser. The abundances of the lightest atomic nuclei preserve another record from an even earlier period. These pieces belong to the model usually called the hot Big Bang. The word beginning can make that model sound more complete than it really is. The hot Big Bang model is extraordinarily successful at describing the evolution of the universe from an early hot dense state into the cooler, more structured cosmos around us today. But simply running its equations backward does not mean that every earlier moment has been directly observed, or that known physics remains reliable without limit as conditions become more extreme. We already met the first major electromagnetic barrier at recombination. That is when the universe became transparent enough for the photons of the cosmic microwave background to travel freely. Those photons give us the earliest electromagnetic image available to astronomy. But the history does not begin there. Long before atoms could remain intact, the universe was hot enough for matter to exist in very different forms. And although we cannot photograph those earlier periods with ordinary light, some of their consequences survived. One of the clearest examples is written into hydrogen and helium. During the first few minutes of cosmic history, the universe was hot and dense enough for nuclear reactions to occur throughout the primordial material. Protons and neutrons could combine. Some formed deuterium, a heavy isotope of hydrogen. Further reactions produced helium nuclei and smaller amounts of several other light nuclei. But the universe was expanding and cooling quickly. The period favorable for this primordial nucleosynthesis did not last indefinitely. Once conditions became too cool and diffuse for the relevant reactions to continue efficiently, the mixture of light nuclei was largely set. Stars later changed the chemical composition of the universe enormously, producing carbon, oxygen, iron, and many heavier elements. But some of the simplest material around us carries a record from much earlier. The predicted primordial amounts of light elements can be calculated using nuclear physics and the conditions expected in a hot, expanding universe. Astronomers can then compare those calculations with measurements of ancient, relatively unprocessed material. The agreement is one of the important reasons cosmologists have confidence that the early universe really passed through this hot nuclear phase. It is another case of learning about a time we cannot directly photograph by examining something that survived from it. Continue backward still, and the reconstruction becomes more difficult. Temperatures rise far beyond anything found in stars today. Atoms cannot exist. Earlier still, even atomic nuclei cannot remain assembled in their later forms. The physics increasingly becomes the physics of particles and fields rather than the astronomy of familiar objects. So our evidence changes character. Instead of collecting an image of an object from that era, cosmologists test whether models of early conditions produce the later records that actually survive. This is the same distinction we have been building throughout the journey. Direct observation is not the only route to knowledge, although inference still has limits. If a model produces a measurable consequence that survives to the present, we can search for that consequence. If several independent observations point toward the same history, confidence can grow. But the farther backward we extrapolate beyond directly tested conditions, the more careful the language has to become. This becomes especially important when the story reaches cosmic inflation. Inflation is the name given to a proposed period of extraordinarily rapid expansion very early in cosmic history. It was developed in part to explain features of the universe that would otherwise be difficult to understand, including why the observable cosmos is so close to spatially flat, and why widely separated regions of the cosmic microwave background have such similar properties. Inflation also provides a mechanism by which tiny early fluctuations could become the seeds of later cosmic structure. But there is an important difference between saying that inflation is a useful framework and saying that we have watched it happen. We have not. Researchers continue to test inflationary models through the patterns they predict in the cosmic microwave background and through other possible primordial signals. Different versions of inflation make different predictions, and the physics responsible for the proposed expansion has not been identified with certainty. So this region of the timeline has to be reconstructed from traces left much later. And if we push still farther backward, the uncertainty grows again. General relativity describes gravity with remarkable accuracy on large scales. Quantum physics describes particles and fields with remarkable accuracy on very small scales. But the earliest conditions we can imagine eventually force both descriptions into the same problem. Density and temperature become so extreme that gravity should have to be treated quantum mechanically. We do not yet possess a complete experimentally confirmed theory of quantum gravity. The safer statement is simpler. The farther backward we follow the well-tested history of the hot expanding universe, the hotter and denser it becomes. We have strong surviving evidence from the cosmic microwave background. We have evidence from primordial nucleosynthesis. We have measurements of cosmic expansion and the distribution of matter. Together they allow us to reconstruct a remarkable amount of the past. But they do not provide a camera pointed at the absolute beginning. And they do not yet tell us, with experimental certainty, whether the phrase before the Big Bang even describes a physically meaningful question. That may depend on physics we have not yet learned. The Big Bang model tells us a great deal about the evolution of our observable universe. It tells us that the cosmos was once hotter and denser. It connects the expansion we measure today with ancient radiation and the primordial abundance of light elements. It gives us a coherent history stretching back far beyond the first stars. But that history still arrives through evidence inside the region we can observe. And that raises a different question. When we say the universe, how much of it are we actually talking about? The cosmic microwave background surrounds us in every direction. Beyond the galaxies we can see today are regions whose light has had more time to travel than the age of Earth, the Sun, or the Milky Way. Yet even that immense visible domain is defined by a simple condition. Information has had enough time to reach us, while much more universe may exist beyond the region we can observe. The next boundary is therefore not a wall in the distant sky, and not a moment buried in the past. It is the boundary of our observable universe itself. The observable universe has an edge, but there is no reason to expect a wall there. That edge exists because light travels at a finite speed, and the universe has existed for a finite amount of time. Every observation we make depends on those two facts. When you look at the moon, you see it a little more than a second in the past. Sunlight takes a little over 8 minutes to reach Earth. Light from nearby stars may have spent years traveling toward us, while the light of a distant galaxy can spend billions of years crossing the expanding universe before it reaches a telescope. The farther we look, the older the information becomes. Eventually, we reach a limit. There has only been so much time for signals to travel since the early universe, so there are regions from which information has not yet been able to reach us. Everything from which a signal could have arrived by now belongs, in the broadest sense, to our observable universe. This leads to one of the stranger numbers in cosmology. The universe is about 13.8 billion years old, yet the radius of the observable universe today is much larger than 13.8 billion light-years. It is roughly 46 billion light-years, a value that can sound impossible at first. If nothing carrying ordinary information travels faster than light, how can we observe matter that is now more than 13 billion light-years away? The answer is that the light did not travel across a universe that remained the same size during its journey. Space expanded while the light was moving. Imagine a very distant region sending photons toward the location that would eventually contain the Milky Way. The photons begin their journey when the universe is much younger. During the billions of years that follow, they continue moving locally at the speed of light, but the cosmic distances between widely separated regions are also changing. By the time those photons finally reach us, the region that emitted them can be much farther away than the simple light travel time would suggest. So there are several different distances hiding inside the ordinary question: how far away is that galaxy? We can ask how long its light has been traveling. We can ask how far away the galaxy was when that light was emitted. Or we can ask how far away the region associated with that galaxy is today, after the universe has continued expanding during the journey. For nearby objects, these distinctions are small enough that we often ignore them. Across cosmological distances, they become essential. This is why a galaxy whose light has traveled for more than 13 billion years is not simply 13 billion light-years away in the present-day sense. Cosmic distance depends on exactly what we are measuring. And once this is clear, the observable universe becomes easier to imagine. We sit at the center of our own observable region, but there is nothing cosmically special about that position. We are at the center for the same reason you are always at the center of everything you can see around you. Observation is centered on the observer. A galaxy billions of light-years away would have its own observable universe centered on itself. Some regions visible to us would also be visible to observers there. Other regions would belong only to their observable domain, and they could receive light from places whose signals have not yet reached us. This means that the edge of our observable universe is not the edge of all existence. It is an edge in our access to information. Beyond it may be more space, more matter, and perhaps more galaxies. How much more is one of the questions we cannot answer directly. The entire universe could be vastly larger than the observable portion. Some cosmological models naturally allow the entire universe to extend without end. Other possibilities involve a universe that is finite in total volume without having an ordinary edge. The observable universe is finite because causal signals have had a finite amount of cosmic time to reach us. Whether the entire universe is finite remains unknown. That distinction prevents a common picture from becoming misleading. Diagrams of the observable universe often show Earth at the center of a giant sphere, with nearby galaxies around us and the cosmic microwave background near the outer boundary. The diagram is useful, but it can accidentally suggest that we occupy the center of the universe itself. We do not have evidence for that. We occupy the center of the particular past light cone from which information is reaching us. Any observer anywhere else would occupy the center of their own. There is another subtlety. The regions that make up the present boundary of our observable universe are not the same thing as the glowing surface of last scattering we discussed earlier. The cosmic microwave background marks the farthest surface we can directly observe using ordinary electromagnetic radiation, because the earlier universe was opaque to freely traveling photons. The broader concept of a particle horizon concerns the maximum distance from which any causal influence could have reached us over cosmic history. Different messengers could, in principle, carry information from epochs earlier than the microwave background. Neutrinos stopped interacting freely with matter much earlier than photons did. Primordial gravitational waves, if they exist at detectable levels, could also carry information from conditions earlier than recombination. For now, those possibilities remain far more difficult to observe than the microwave background. But they remind us that a horizon can depend partly on what messenger we are using. Visible light has one practical boundary. Microwaves carry us to the surface of last scattering. Gravitational signals may eventually allow us to investigate still earlier conditions. Yet even if our instruments became perfect, the finite history of causal contact would remain. Some regions are simply outside the domain from which information has reached us so far. And this creates a peculiar kind of humility. We cannot select among such possibilities by looking directly at those regions, because their information is not here. Science can constrain what is plausible by studying the geometry, statistics, and physical laws inside the observable universe. But direct descriptions of specific objects beyond the horizon would be speculation. This is where the difference between an unknown object and an inaccessible region becomes especially clear. Dark matter is invisible, but its gravity acts within the region we can observe. A black hole hides events behind its horizon, but the black hole's exterior gravitational field remains observable. The early plasma blocks our electromagnetic view, but its later radiation carries a surviving record. Beyond our present cosmic horizon, we face something else. There may be no signal here to analyze at all. And yet even this boundary does not remain fixed in the simplest possible way. As cosmic time passes, light from some regions that has not reached us today may eventually arrive. Our past light cone continues growing. But the universe is also expanding, and observations show that the expansion is accelerating. Those two processes create a more complicated future than the simple idea that we will eventually see everything. Some very distant regions are being carried away from us by cosmic expansion in such a way that signals they emit sufficiently late will never reach us, even given unlimited time. This introduces another horizon, a limit associated with what can ever communicate with us in the future. The distinction between those horizons is easy to lose because both involve distances far beyond anything human beings can travel. But they ask different questions. The particle horizon asks how far information could have traveled to us from the past. A cosmic event horizon asks which events occurring now or in the future can ever send us a signal. The particle horizon is defined by signals that could have reached us already, whereas the cosmic event horizon concerns which future events can ever affect us. And somewhere between them lies one of the central mysteries of modern cosmology. The expansion of the universe is not simply continuing. It is accelerating. We can measure that acceleration through the behavior of distant objects and through increasingly detailed maps of cosmic history. But the name given to whatever is responsible does not explain it. We call it dark energy. And once again, astronomy has given a name to something long before it has understood what that thing really is. For a long time, the simplest expectation was that cosmic expansion should gradually slow down. The universe contains matter, and matter attracts matter through gravity. Galaxies might continue moving apart, but the mutual gravitational influence of everything in the cosmos should resist that expansion. The question seemed to be how much the expansion would slow, and whether there was enough matter for it eventually to stop. Then astronomers began measuring explosions in very distant galaxies. The explosions were Type Ia supernovae, a class of stellar event whose brightness can be calibrated well enough to make them useful for measuring enormous cosmic distances. By comparing how bright one of these supernovae should be with how faint it appears from Earth, astronomers can estimate how far away it is. Its spectrum also provides a redshift, which tells us about the expansion of the universe during the light's journey. In the late 1990s, two teams used distant supernovae to investigate how the expansion rate had changed over cosmic history. They expected to measure deceleration. Instead, the distant supernovae appeared farther away than the expected slowing models predicted. The universe had not simply continued expanding. At relatively recent cosmic times, that expansion had begun accelerating. Gravity had not disappeared. Galaxies still attracted one another. Stars still orbited galactic centers. Galaxy clusters remained gravitationally bound. On those scales, local gravity continued doing what it had always done. But across the largest distances, the average expansion of space was behaving differently. Something in our description of the cosmos was missing. The name given to that missing piece was dark energy. The name can make it sound as if astronomers discovered a new substance and placed it in a container. They did not. Dark energy is the name used for whatever is responsible for the observed accelerated expansion, whether that turns out to be a property of empty space, a field that changes with time, some modification in our description of gravity on enormous scales, or something we have not yet considered correctly. The acceleration is observed through the expansion history, while dark energy is the name for the unresolved cause. The simplest version has been sitting inside Einstein's equations for more than a century. It is called the cosmological constant. In this model, there is a fixed energy density associated with empty space. It does not thin away as ordinary matter becomes more dilute during cosmic expansion. If the universe grows, there is simply more space containing that same constant energy density. At early times, matter was much denser than it is today, so its gravitational influence dominated the cosmic expansion history. As the universe expanded, matter became more spread out. A constant dark energy component did not dilute in the same way. Eventually, its influence became dominant, and cosmic expansion began accelerating. This version forms part of the standard cosmological model known as lambda CDM. Another possibility is that dark energy is not constant, and that its behavior changes as the universe evolves. A changing component is sometimes modeled through fields rather than through a fixed cosmological constant. There are many possible versions, and the details matter because different models produce slightly different expansion histories. That means the universe itself becomes the experiment. If dark energy has behaved differently at different times, then a sufficiently precise map of cosmic expansion should contain evidence of that change. This is where the dark energy spectroscopic instrument enters the story. DESI observes from the Nicholas U. Mayall telescope at Kitt Peak in Arizona. Rather than concentrating on one extraordinarily distant galaxy, it measures enormous numbers of galaxies and quasars across the sky. For each target, its spectrum provides a redshift. Redshift gives astronomers a way to place the object along the line of sight within a cosmological model. Repeat that measurement millions of times, and individual galaxies become points inside an enormous three-dimensional map. By April of 2026, DESI had completed the observations originally planned for its 5-year survey ahead of schedule, after measuring spectra for more than 47 million galaxies and quasars. The instrument had effectively turned a large fraction of the accessible sky into a record of cosmic structure across time. If you enjoy these slow journeys through cosmology, you can subscribe, and there will be another one waiting whenever you want it. The important feature in that map is not simply the location of each galaxy. It is the pattern formed by millions of them. Long before galaxies existed, the young universe contained a hot plasma of matter and radiation. Density disturbances move through that plasma as pressure waves, leaving behind a characteristic scale known as baryon acoustic oscillations. We met the same early plasma while discussing the cosmic microwave background. When the universe cooled enough for atoms to form and photons began traveling freely, those acoustic waves stopped propagating in the same way, but their preferred scale remained imprinted in the distribution of matter. Billions of years later, galaxies retain a faint statistical memory of that scale. There is a slightly enhanced probability of finding galaxies separated by a particular distance. Because the original physical scale can be calibrated from early universe physics, cosmologists can use it as a standard ruler. Now imagine finding that ruler at several different periods in cosmic history. Its apparent size along and across our line of sight depends on cosmic distances and on how rapidly the universe was expanding at those times. Measure the pattern over many redshifts, and the expansion history begins to emerge. This is one of DESI's primary methods. The remarkable part is that the ruler was created before there were galaxies, yet galaxies billions of years later still carry its imprint. Once again, information survives by changing form. A sound wave in primordial plasma becomes a statistical preference in the spacing of galaxies. Astronomers measure that spacing, compare it across cosmic time, and use it to test the physics governing the expansion of space. DESI's early results agreed broadly with the standard lambda CDM model when considered on their own. But when the first 3 years of DESI measurements were combined with observations of the cosmic microwave background and Type Ia supernovae, the combined data strengthened indications that a model with dark energy changing over time might fit better than a strictly constant version. This attracted considerable attention because the cosmological constant is not merely one explanation among many. It is a central part of the standard model. If dark energy truly changes with time, cosmology would need to explain what is changing, why it changes, and how that behavior connects with the rest of fundamental physics. But this is exactly the kind of moment when careful language matters most. The result is not a discovery that dark energy evolves. The evidence depends on combinations of datasets and on the models used to interpret them. And newer measurements have already made the picture less simple. In July of 2026, DESI researchers released a more precise analysis using the Lyman alpha forest, a pattern of absorption created when light from extremely distant quasars passes through intergalactic hydrogen. These observations probe a much earlier period of cosmic history than nearby galaxy surveys. The new analysis extracted more information from the distribution of that hydrogen than earlier measurements had used. Its result moved closer to the prediction of the standard lambda CDM model. That does not erase the earlier evidence, suggesting evolving dark energy. It means the complete set of observations is not yet telling one simple story. Perhaps the hints of evolution will weaken as the measurements improve. Perhaps a changing dark energy model will survive. Perhaps the eventual explanation will require something more complicated than either of those options. DESI's completed 5-year dataset is still being processed, and its first full survey dark energy results are expected in 2027. For now, the uncertainty is real. And this uncertainty affects more than our description of the present. If the acceleration continues, then the distant future of the observable universe will be very different from its past. There are galaxies whose ancient light reaches us tonight, but whose much later signals may never arrive. As space continues expanding, our causal connection with distant regions can change. The sky available to observers in the far future may contain less information than the sky available to us now. So the next boundary is no longer only about how far our telescopes can see. It concerns which parts of the universe can remain connected to us at all. The expansion we cannot yet fully explain is slowly changing the answer. A galaxy can be visible to us tonight and still be too far away for a message sent from Earth today ever to reach it. Cosmology changes that intuition. The space between distant galaxies is not static while light moves through it. The universe continues expanding, and the rate at which cosmic distances change depends on the history of that expansion. So there are several different questions hidden inside the simple phrase, far away. Can we see the object now? Could a signal we send now ever reach it? Will light emitted by the object today eventually reach us? And if neither side sends anything yet, could the two regions ever exchange information at some later time? Those questions do not always have the same answer. Start with the easiest one. A galaxy is visible today because some light from it has already completed the journey to us. The image may be enormously old. If its light traveled for billions of years, then we are seeing the galaxy as it existed billions of years ago. During all of that time, the universe kept changing. The distance between us and the region containing that galaxy changed, and the galaxy itself continued evolving. The photograph is therefore evidence of an old connection. It does not guarantee a future one. This is where a useful but often confusing boundary appears. At any moment in cosmic history, astronomers can define something called the Hubble sphere. Very roughly, it is the distance at which the recession rate associated with cosmic expansion equals the speed of light. It is tempting to treat that distance as the edge of visibility. But it is not. A galaxy can recede from us at a rate greater than the speed of light because the recession comes from the changing cosmic distance between widely separated regions, rather than from the galaxy locally racing through its near base faster than a light beam. General relativity allows this without requiring any object to pass a local observer faster than light. and light emitted from beyond the Hubble sphere can sometimes still reach us. The reason is that the Hubble sphere itself changes as the universe evolves. So the Hubble sphere is useful for describing expansion at a particular time, but it is not a permanent wall separating what can and cannot communicate with us. For that, we need a different boundary known as the particle horizon, which looks backward through cosmic history. It marks the limit of the region from which a causal signal could have reached us during the history of the universe up to the present. This is closely connected to the observable universe we discussed earlier. As time passes, our past light cone continues to grow. New light arrives. We receive later portions of old stories from distant places, and in some cases, information from regions that had not yet had enough time to communicate with us can enter our observable history. If expansion behaved in a sufficiently simple way, it might be tempting to imagine that patience would eventually solve the problem. As time passes, more light arrives, which might suggest that unlimited patience would eventually make every sufficiently distant region visible. But an accelerating universe does not offer that future. Acceleration introduces a cosmic event horizon. This horizon asks a different question from the particle horizon. This horizon asks which events can ever affect us even if we wait indefinitely. The distinction becomes easier to understand if we imagine a distant galaxy sending two signals. One signal left billions of years ago. That ancient light may already be approaching the Milky Way, and perhaps it reaches us tonight. Now imagine that the same distant region sends another signal today. The second signal begins its journey in a universe much larger than the one through which the first signal traveled. If the region is sufficiently distant and cosmic acceleration continues in the appropriate way, the new signal may never arrive. The ancient galaxy remains visible because we are receiving its past. Its present may already lie outside our future causal reach. That is one of the quietest strange facts in cosmology. A telescope can show us something with which we can no longer exchange new information. The image is almost like a letter from a country whose road has disappeared while the letter was traveling. We continue receiving messages that began before the connection was lost. The difference is that there is no road to rebuild. The separation comes from the geometry and future expansion of the universe itself. Now consider the problem from our side. Suppose we send a beam of light toward a sufficiently distant galaxy today. The beam always moves locally at the speed of light. The beam encounters no local malfunction or physical barrier, yet reaching the galaxy still depends on the entire future history of the space between us and the destination. If the intervening cosmic distance grows in the wrong way, the light never catches up. So visibility does not guarantee reachability. There are galaxies we can observe whose old photons reach Earth, while signals launched from Earth now could never arrive there. And the same logic works in reverse. Some of those galaxies may currently receive ancient light from the region that would become the Milky Way, while being permanently cut off from signals we generate much later. The universe can therefore preserve a shared past while removing a shared future. This is why the phrase observable universe can conceal more complexity than it seems to contain. Observability and reachability therefore change differently as the expansion history unfolds. And neither should be confused with the total universe, which may extend far beyond every region with which we can ever communicate. The boundaries are also centered on the observer. An astronomer in a very distant galaxy has their own past light cone and their own cosmic horizons. Their accessible region overlaps with ours in some places and differs in others. There is no single transparent sphere drawn through space for everyone to share. Each observer's causal history is built from the signals that can reach that observer. This brings us back to dark energy. If the accelerated expansion is produced by something close to a cosmological constant, then acceleration continues into the distant future. Widely separated galaxies that are not held together by gravity become increasingly isolated from one another. Their light becomes progressively more redshifted as the universe expands. As expansion continues, the light stretches to longer wavelengths, carries less energy per photon, and becomes increasingly difficult to detect. For observers in the far future, much of the large-scale universe that is visible to us today would become extraordinarily faint. Distant galaxies would not all suddenly switch off at a particular moment. Their information would fade into longer wavelengths and lower energies, while later emissions from sufficiently distant regions would never arrive at all. Locally bound structures behave differently. Local systems such as the Solar System, the Milky Way, and the Local Group remain gravitationally bound. Because cosmic acceleration dominates only across sufficiently large separations where local binding does not overcome the expansion. So the far future is not one in which every star instantly drifts away from every other star. It is a future in which gravitational islands become increasingly isolated from other gravitational islands. Each gravitational island keeps part of the universe nearby, while the spaces between islands grow and the information connecting them becomes poorer. There is an unusual consequence hidden inside that future. Astronomers alive in an extremely distant era could have better technology than anything we can imagine, and still possess less direct evidence of the wider cosmos than we do. The cosmic microwave background would be enormously redshifted and harder to detect. Remote galaxies would have faded from accessible wavelengths. Much of the evidence that allows us to reconstruct cosmic expansion would no longer be sitting plainly in the sky. Even with better instruments, observers in that distant era would receive fewer messages from the wider universe. This makes the cosmic event horizon feel very different from the black hole horizon we began with, even though the language is similar. A black hole creates a boundary around a compact region where future-directed signals cannot return to distant outside observers. A cosmological event horizon emerges from the large-scale evolution of space-time and determines which sufficiently distant future events can ever communicate with us. One surrounds a black hole. The other is woven into the expansion history of the cosmos around the observer. But both force us to think about information in the same unusual way. The important question is not simply where something is. We also have to ask whether any future path carrying information connects that place to us. At human scales, that question almost never matters. Across the universe, that question changes what distance can mean. There are places we have never seen but may someday receive information from. There are places we see tonight whose later history will never reach us. And there are regions beyond all of those, part of whatever larger universe exists outside the domain that can ever become connected to our own world line. The sky is therefore an archive whose contents are still arriving. Some pages have been traveling toward us since before the sun existed. Others have not reached us yet. And some pages are being written in places from which no future copy can ever arrive. Once that distinction becomes clear, the next question is almost unavoidable. If there are limits that no amount of waiting can overcome, what happens when our instruments finally approach the other boundaries that physics has placed in front of them? Telescopes can grow larger, detectors can become colder, mirrors can be placed farther from Earth, and new messengers can be discovered. But eventually the problem may stop being the instrument. Eventually the universe itself decides what information exists for us to collect. In January of 2026, astronomers announced that the James Webb Space Telescope had confirmed a galaxy called MOMZ-14. The light-reaching Webb had begun its journey when the universe was only about 280 million years old. That is an extraordinarily early time. The universe had already become transparent to light, stars were forming, and galaxies had begun assembling, but almost all of cosmic history still lay ahead. The sun would not exist for more than 9 billion years. Earth would come later still. MOMZ-14 is faint in the image. There is no enormous spiral structure filling the frame, and no bright stellar disk resembling the Milky Way. What matters is the distance encoded in its spectrum. Its measured redshift places it farther back in cosmic history than any spectroscopically confirmed galaxy known at the time. A telescope built by people on one planet had received enough photons from that galaxy to identify it across more than 13 billion years of cosmic evolution. And Webb was able to do this partly because its designers understood what expansion does to ancient light. Very distant galaxies originally emit large amounts of radiation at shorter wavelengths. But while that light crosses the expanding universe, its wavelengths stretch. The farther the light travels through cosmic expansion, the greater that redshift can become. By the time radiation from the earliest galaxies reaches us, much of the light that began at visible or ultraviolet wavelengths has moved into the infrared. That is where Webb was designed to look. Its primary mirror is 6.5 meters across, giving it a much larger collecting area than Hubble. Its instruments are sensitive to infrared radiation, and much of the observatory is kept extremely cold, so that heat from the telescope itself does not overwhelm the faint infrared signals arriving from space. These are difficult problems, but they belong to the category of problems that engineering can attack. Build a larger mirror and more photons can be collected. Improve a detector and weaker signals may become measurable. Cool the instrument and thermal noise can be reduced. Observe longer and a faint source may emerge from the background. Place the telescope in space, and Earth's atmosphere no longer blocks the same parts of the spectrum. Use gravitational lensing from a foreground cluster, and nature itself can sometimes provide additional magnification. But there is a point where improving the telescope stops solving the actual problem. We have already encountered one such point. The cosmic microwave background comes from roughly 380,000 years after the beginning of cosmic expansion. Before that era, free electrons repeatedly scattered photons. The universe was filled with radiation, but it was opaque. Even a telescope with a mirror many times larger than Webb, perfect detectors, no instrumental noise, and unlimited observing time could not take an ordinary electromagnetic photograph through the primordial plasma before recombination. The problem would no longer be sensitivity. The photons carrying a clean image from behind that layer do not exist for us to collect in the required form. Light from earlier times was repeatedly scattered. Its original directional information was lost in the plasma. The surface of last scattering is therefore different from a faint galaxy. Greater sensitivity can help with a faint galaxy, while the opacity of the early universe removes the directional photon record an electromagnetic telescope would need. That difference is easy to overlook because both can appear simply as darkness on an instrument. A faint signal can be an engineering problem. Here, the limitation is that this kind of photon cannot carry the requested directional information to us. A similar distinction appears at a black hole. Suppose we built an optical instrument larger than the solar system. Suppose its resolution were limited by nothing we know how to engineer. It might study the surroundings of a black hole with extraordinary precision. It could follow matter closer to the horizon. It could examine gravitational lensing and the changing plasma around the object. But it could not receive a photograph sent outward from an event after that event had crossed the horizon. There is no optical improvement that changes the causal structure of the black hole. No outward path exists for the signal, regardless of the telescope's resolution. And now the cosmological horizon gives us a third version of the same idea. A sufficiently distant future event may lie beyond our cosmic event horizon. A photon emitted there can behave perfectly normally in its local region. It can move at the speed of light. Nothing needs to absorb or destroy the photon. Cosmic expansion alone can prevent it from ever reaching us. Yet the future evolution of cosmic distance may prevent that photon from ever entering our location. An infinitely sensitive detector on Earth would still record nothing from that event. The detector cannot measure a signal that never arrives. These limits belong to different pieces of physics, but they share one feature. They cannot be defeated merely by collecting more light. Another messenger may sometimes pass through conditions that stop the first, so reaching a boundary with one kind of signal does not end the investigation. We saw this with gravitational waves. Hot matter and dust can make electromagnetic observations difficult, but gravitational waves travel through matter with very little interaction. The early universe offers a similar possibility. Photons began moving freely through the cosmos after recombination. Other particles stopped interacting freely much earlier. Neutrinos are extraordinarily reluctant to interact with ordinary matter. In the early universe, they are expected to have decoupled from the surrounding plasma when the cosmos was roughly a second old. If that ancient background of neutrinos could someday be detected directly, it would provide access to an era enormously earlier than the cosmic microwave background. There is good reason to expect such a cosmic neutrino background from standard cosmology. But directly detecting those ancient neutrinos is an entirely different challenge. Today their energy should be extremely low. Neutrinos interact so weakly that the property allowing them to carry ancient information also makes them very difficult to catch. The message may exist. Our instruments may simply not yet know how to read it. That is an engineering boundary, at least in principle. There may be another messenger from the early universe as well. If some models of cosmic inflation are correct, the very early universe could have produced primordial gravitational waves. Those waves could have left characteristic patterns in the polarization of the cosmic microwave background. Experiments have searched for such signatures for years. A convincing primordial gravitational wave signal has not yet been established. But the search illustrates something important about the way cosmology progresses. We may never photograph inflation. We might instead discover a surviving consequence of it. Once again, the universe may tell us about an inaccessible era without giving us a direct image of that era. The deepest observational limits, therefore, have to be described carefully. There is a difference between a signal that exists but is too faint for today's instrument and a signal that physics prevents from reaching us in the form we want. There is also a difference between direct information being unavailable and all information being unavailable. The universe may hide a region while leaving consequences outside it. It may erase an image while preserving a statistical pattern. It may block photons while allowing another messenger to escape. And sometimes it may truly place events outside every possible causal connection with us. The challenge is knowing which kind of boundary we have reached. That question becomes increasingly important as astronomy improves, because every new instrument removes some practical limitations. If a source is too faint, better sensitivity can help. If angular resolution is poor, a larger effective aperture can help. If dust blocks visible light, infrared or radio observations can help. If Earth's atmosphere absorbs a wavelength, a spacecraft can move the detector above it. If one messenger interacts too strongly with matter, another messenger may carry information through. But eventually, there are no engineering excuses left. At that point, the issue is the geometry, the history of interactions, and whether information from one event can physically reach another. That is the point where astronomy begins to feel different from exploration on Earth. An unexplored island still exists on the same connected surface as the explorer. A deeper submarine can descend farther into the ocean. A stronger drill can reach deeper underground. Given enough technology, ordinary geographical distance can usually be treated as a practical obstacle. Cosmic distance does not always behave that way. Some boundaries do not mark places that are difficult to visit. They mark relationships that space-time does not permit, and there is something unexpectedly calming about recognizing that limit. It removes the need to imagine that one final telescope will eventually turn the entire universe transparent. Science has never required that promise. We can understand a great deal without having access to everything. The black hole image did not require a camera inside the horizon. The first gravitational wave detection did not require photographs of the merging black holes. The cosmic microwave background does not show us the first second of cosmic history. Dark matter maps do not require dark matter to glow. Our measurements of dark energy do not require us to hold dark energy in a laboratory container. Again and again, knowledge has arrived through consequences. The universe does not always show us the thing itself. Sometimes it shows us what the thing has changed. And when we reach a boundary where a direct signal is missing, that absence can become part of the evidence. Examples include the dark center inside the radio ring, gravitational mass without matching light, the microwave boundary before which photons cannot carry a clear image, and future events whose signals will never arrive. We began this journey by treating those absences as obstacles. But perhaps that is only half of the story. Because once the surrounding physics is understood well enough, what does not arrive can sometimes tell us almost as much as what does. There is a useful difference between an empty measurement and a meaningful absence. If a telescope points toward a patch of sky and records nothing because the exposure was too short, that darkness tells us very little. The detector may simply have failed to collect enough photons. But if we understand what should have been there, understand the instrument, understand the surrounding physics, and still find something missing in a precise and repeatable way, the absence itself can become evidence. That is what happened in the first image we visited. Around the black hole in M87, the Event Horizon Telescope detected a bright ring of radio emission surrounding a much darker central region. The dark center did not reveal the interior of the black hole. It showed the effect produced when light paths near an enormous concentration of mass are bent, redirected, or captured. The shadow could be measured because there was light around it. Without that surrounding emission, the absence would have had no shape. The information came from the relationship between the darkness and what remained visible. Then we moved much farther back in time and found a different boundary. The early universe before recombination was full of photons, but repeated scattering prevented those photons from carrying a clear image across great distances. The cosmic microwave background marks the era when that changed. Once the universe had cooled enough for neutral atoms to form, photons could begin traveling over enormous distances without being continually scattered. Those photons now surround us as microwave radiation. Again, the boundary did not simply end the investigation. The cosmic microwave background contains small variations in temperature and polarization. Those patterns preserve information about conditions in the young universe, including the tiny density differences from which later cosmic structure developed. We cannot turn the cosmic microwave background into a photograph of the first second, but we can study the record carried by the radiation that survived. And before the universe became transparent, other records were already being written. The relative abundance of some light elements preserves evidence of primordial nuclear reactions. The later distribution of galaxies preserves information about acoustic waves in the early plasma. The large-scale structure of the cosmos carries the consequences of small differences that existed long before galaxies themselves had formed. Information does not always survive in its original form. A fluctuation in a hot plasma can become a preference in the separation between galaxies billions of years later. A change in spacetime can become a tiny interference pattern inside a detector. A gravitational field produced by unseen matter can become a distortion in the shapes of more distant galaxies. That last example gave us dark matter. We still do not know the underlying identity of dark matter, while its gravitational role is constrained by several kinds of observation. Galaxies rotate in ways that visible matter alone does not adequately explain. Galaxy clusters bend background light according to more mass than we can account for, with luminous stars and hot gas. In colliding clusters, gravitational lensing can trace mass into regions separated from much of the ordinary interacting gas. None of those observations places a dark matter particle directly into our hands. Together, they constrain what any successful explanation has to accomplish. Any successful dark matter explanation has to supply the additional gravitational influence in the right places and remain consistent with the way cosmic structure forms and behaves. Dark energy gives us an even more abstract version of the same process. There is no dark energy cloud for a telescope to photograph. Instead, astronomers measure distances, redshifts, supernovae, the cosmic microwave background, and the statistical distribution of galaxies across different epochs. Those measurements show acceleration in the expansion history, with its physical cause still unresolved. Calling it dark energy does not fill that gap. It gives the gap a name so that it can be measured more carefully. The standard cosmological model provides one particularly simple description through a cosmological constant, while current observations continue testing whether that description is sufficient. Whatever the eventual answer, the problem was discovered through a mismatch between the expansion history we observe and the behavior expected from a universe containing matter alone. Once more, something absent from a direct image has become visible through consequences. This is where all of the boundaries we have visited begin to look less separate. The black hole prevents certain information from returning. The early plasma prevented photons from carrying a clear image across the young universe. Dark matter does not reveal itself through ordinary emitted light. Dark energy is inferred from the changing expansion of cosmic distances. And the cosmological horizon can remove some future events from our causal reach altogether. Once those differences are recognized, each form of cosmic darkness becomes more specific. We stop treating every invisible thing as though it belongs to the same darkness. The more precise question is why the information is missing. That question often tells us what kind of observation to attempt next. If dust absorbs visible light, look in wavelengths that pass through it more easily. If an object does not shine, measure its gravitational influence. If photons were trapped in an early plasma, search for other relics or for later imprints of the physics from that era. If a distant event lies beyond a true causal horizon, then no improvement in sensitivity will recover a signal that cannot arrive. The method depends on knowing which problem we face. And sometimes the answer is simply that the information is unavailable. Science has to make room for that possibility too. There is no rule promising that every physically meaningful question will eventually produce an observable answer. Some questions may depend on events permanently separated from us. Some may involve conditions where our current theories stop being reliable. Some may leave no unique surviving trace that allows us to choose between competing histories. Recognizing that limit does not undo everything we have learned before reaching it. It tells us where the evidence ends. That boundary between evidence and speculation may be one of the most important things a measurement can reveal. The observable universe is already incomplete. We occupy one location in cosmic history, receive only the signals that can enter our past light cone, reconstruct earlier eras from surviving records, and infer hidden components from the effects they leave on visible things. Yet from those incomplete messages, a surprisingly coherent history has emerged. The universe expanded from a hotter and denser early state. Light began traveling freely, small density differences grew into structure, stars and galaxies formed, black holes appeared and merged, and at later times cosmic expansion began accelerating. None of that requires us to see everything. It requires measurements that agree with one another well enough to tell a consistent story. That may be the quieter lesson behind all of these mysteries. The universe does not owe us a complete view before it becomes understandable. We began with a photograph containing a dark center. Now that darkness looks a little different. It no longer seems like a place where information simply disappears. It marks the boundary between what can arrive directly and what has to be reconstructed from everything around it. And once we accept that distinction, there is one final question left. If our picture of the universe will always be incomplete, what does it mean to live inside that incomplete picture? The answer does not require another detector. It begins with the light that has already reached us. Every piece of astronomy begins with something arriving. A photon reaches a mirror, a radio wave reaches an antenna, a gravitational wave passes through an interferometer, or a particle crosses a detector. The event that created the signal may have happened before human beings existed, before Earth existed, or before the first stars had begun to shine. Yet for us, the information becomes part of the observable universe only when the connection is finally completed. The night sky is an accumulation of arrivals. Nothing we see is perfectly current. The moon is already slightly in the past, the sun is several minutes in the past, and the nearest stars are years in the past. Across greater distances, the delay becomes millions and then billions of years, so we are surrounded by old information. And the farther outward we look, the deeper that archive becomes. Some photons began traveling when galaxies looked very different from the galaxies around us now. Others left their sources before the sun formed. The microwave radiation filling the sky has been moving freely since the universe first became transparent to light. Every signal carries only what survived the journey. Some wavelengths are absorbed, some photons are scattered or bent by gravity, and some signals never begin a path that can reach us. And some information was created in regions whose geometry prevents it from ever reaching this part of the universe. Our cosmic history is therefore built from surviving signals, which means astronomy has always worked with partial evidence. Different measurements, made with different instruments and based on different physical effects, begin to overlap. That overlap is where confidence comes from. We do not need one perfect window onto the universe. We need independent pieces of evidence that continue fitting together when the measurements improve. Sometimes the measurements do not fit, and that can be useful. A mismatch can reveal a mistake in a model, a problem in a measurement, or something missing from our description of nature. Dark matter entered cosmology because visible matter did not provide enough gravity to explain a growing collection of observations. Dark energy entered because the measured expansion history did not behave as a matter-only universe would have been expected to behave. Those names did not solve the mysteries. They marked places where the accounting failed and where the model still needed an explanation. There is no requirement to fill every unknown with a confident answer. We can say that dark matter produces gravitational effects without pretending to know its underlying identity. We can say that cosmic expansion is accelerating without pretending that the physics of dark energy is settled. We can reconstruct an early hot universe without claiming to have observed an absolute first instant. We can describe an event horizon without pretending to know what a complete theory of quantum gravity would say about every condition inside a black hole. The edges of knowledge can be mapped, which makes the boundary between evidence and uncertainty clearer. Some limits come from technology or weak signals and may move as instruments improve. Others come from the messenger we chose, or from the causal structure and history of the universe itself. A telescope can become more sensitive, but it cannot receive a photon that never reaches it. A detector can operate longer, but waiting cannot create a future connection that spacetime does not permit. The distinction may feel disappointing if we imagine science as a process that must eventually uncover everything. But there was never any reason to expect that. We are physical observers inside the system we are trying to understand. We are not looking at the universe from somewhere outside it. Our clocks belong to cosmic history, and our detectors occupy particular locations. Every measurement is limited by the paths along which information can reach those locations. Even the concept of the observable universe is built around that fact. There is a region connected to us by past signals. Beyond it may be more. Some of that more may eventually become accessible to observation, may remain outside every possible future exchange with us. And the entire universe may be much larger than the region our observations will ever contain. We do not know. For a while, that can feel like a reduction. A smaller claim than the one we might prefer. But it also gives the observable universe a different kind of intimacy. This portion of cosmic history is not merely the part our telescopes happen to find first. It is the part that has been able to communicate with us. Every star we observe belongs to that network of causal connections. Every galaxy in a deep field image has sent something across the intervening space. Every ancient microwave photon reaching a detector has completed a path extending across almost the entire history of a transparent universe. The connection may be extraordinarily weak. It may consist of a few photons collected over hours. But it exists. And because it exists, part of the history of a distant place can become part of ours. Perhaps somewhere tonight, a photon is approaching Earth after traveling for billions of years. It has crossed expanding space while galaxies formed, collided, and changed. It may have passed through regions filled with gas, and through enormous stretches where almost nothing interrupted its path. Its wavelength has been stretched by cosmic expansion, and gravity may have bent its route. The source that produced it may no longer look anything like the source encoded in the light. For nearly all of that journey, Earth was irrelevant. The photon was not heading toward humanity in any meaningful sense. There was no destination waiting for it, only a path through space-time that eventually intersects a planet. Perhaps the photon enters the mirror of a telescope. Perhaps it reaches a detector built to recognize the wavelength it now carries. An electrical signal appears and the data are stored. Later, someone compares that tiny event with millions of others. The photon becomes one point in a spectrum, one pixel in an image, or one contribution to a measurement that would have been impossible without it. Nothing about the moment looks cosmic. There may be no dramatic sound or visible flash, just a telescope continuing to track and a detector continuing to count as ancient information finally arrives. There will always be other photons that do not. There will be regions whose messages are too faint, too scattered, too old, or forever outside our causal reach. There will be questions for which nature gives us only indirect traces. Perhaps there will be questions for which no accessible trace survives at all. The picture will remain incomplete, yet the portion that reaches us already contains black holes, ancient radiation, invisible mass, accelerating expansion, and a history stretching almost to conditions where our present theories begin to lose their certainty. All of it has been reconstructed from signals that managed to cross the distance. So perhaps the final boundary is not something we need to defeat. It is simply part of what it means to observe a universe from within. We receive what can reach us, measure it as carefully as we can, and learn to recognize what is missing. And somewhere above a quiet Earth, one more ancient photon finishes its journey.